Okay, I'm back to your reference table, page 15. This one, we're looking at your planets. So if I'm looking at my inner planets, make sure you realize that the first row is the sun. Sun is not a planet, it's a star. Your inner planets are also known as your terrestrial planets. That's your Mercury, Venus, Earth, and Mars. If you look at those, you'll notice that their equatorial diameter are relatively small. If you look at the last column of density, those have a higher density. They're terrestrial, that means land. All right. Outer planets, known as Jovian planets, Jupiter, Saturn, Uranus, and Neptune, if I have you look at the equatorial diameter of those, you'll notice they're a lot larger than your terrestrial planets. If you look at your density, you'll notice they're less dense. That's because they're gaseous. If you look at the equatorial diameter, they're a lot larger than terrestrial, but their density is smaller. Planetary models, also in your vocab. Geocentric was the belief, I'm sure you guys talked about in social studies, like science was not a big thing until the Enlightenment, 1500s, 1600s. So the whole idea is they used to think that all planets, stars, everything revolved around the Earth, hence geo, meaning Earth, centered. So the Earth is in the center, Earth is the blue, our sun is the yellow, any planet, everything revolved around us. The only problem is it didn't explain retrograde. The planets go into retrograde. Remember, they're slowing down, but they look like they're going backwards. Heliocentric, helio, sun. Sun is the center of the solar system. Nicholas Copernicus, 1600s. The whole idea, this does explain why there's retrograde between the planets. So there's times that when the planet's further away from the sun, there's not as much gravitational attraction. With that one, it's slowing down. When the planet gets closer to our sun, it actually has a greater gravitational attraction and it gets pulled faster or moves faster because it's got a greater pull. Same thing, sun is in the center and then all the planets orbit the sun. All right, stars and galaxies. Star, you're looking at, it's a body of gas. It's going to give off a ton of energy, either in heat or light. If you look at stars, they vary in color because of the temperature, the mass, and the size. If you're on your handy dandy Earth Science reference table, page 15 at the top, characteristic of stars, it has luminosity, and then in little parentheses they tell you what luminosity is, a rate at which a star emits energy relative to the sun. So how bright it is. At the bottom, you'll see it says surface temperature. Unlike most graphs, what you'll notice is the highest value on the x-axis is on the left side, and the lowest value is on the right side. Your vertical or your y-axis, also, just like when we did your stream velocity, they're not equally spaced. Neither is your x-axis. So I need you looking at your reference table, looking at find Rigel, read straight down, tell me the color. You should see it's a blue-white. Find Polaris, read straight down. Polaris is a yellow star. Find our sun, read down. Our sun also is a yellow star. find Betelgeuse. Betelgeuse all the way in the top right corner. Read down. It's an orange-red star. Now, if I'm looking at those three stars, which of the three has the greatest luminosity? So in other words, which one's highest? And that will be Betelgeuse. Betelgeuse slightly higher than Rigel. If you look at Polaris, Polaris not as bright. You look at our sun is not as bright as Polaris. The brighter the star, or the more luminosity, the quicker that star is going through its energy. It's burning up its energy. It takes a lot of energy to give off that light. Next year in chemistry, you guys will do a lab with using a spectrometer. It's going to separate light into different colors or wavelengths. Scientists or astronomers use this really quick to get the absorption, the dark line spectrum. This one, we're going to try to figure out what the composition of the star is, what the temperature of the star is. With that one, most stars are made of two elements, hydrogen and helium. We found with technology that stars actually do rotate, they will revolve around another star, and they're either moving towards or away from the Earth. Using the spectrum, the scientists can figure out, is the star moving closer to the Earth or moving further away from the Earth? The further it's moving, the longer the wavelength. The closer it's moving, the shorter the wavelength. So I'm going to need to go on your reference table, page 14. So on page 14 of your reference table, I need you on the electromagnetic spectrum. It's on the bottom. Looking at visible light. Notice as I go to the left side, my wavelength is decreasing. If I go towards the right side, my wavelength is increasing. In the visible light spectrum, the blue end or the violet end of the spectrum has got a shorter wavelength. Whereas the red end of the spectrum has got a longer wavelength. So if we are actually using the Doppler effect to see if the stars are coming closer to us or further away from us, what we've noticed is that the stars are actually moving further away from us. So we're shifted towards the red end of the spectrum, or we would say it has a red shift to the spectrum. It just shows that the wavelength is getting longer, so it shows distance. Speaking of distance, the distance we measure using for stars is in light years. So light years, how far light travels in 1 year. All right, so the speed of light is 300,000 kilometers per second. Times that by the number of seconds in a year, comes out to approximately 9.5 trillion kilometers the light travels in 1 year. So if you're looking at our sun right now, you're looking outside, the sun is out. The sun that you currently see right now took 8 minutes and 20 seconds to get here. So it left 8 minutes and 20 seconds ago. Polaris. Polaris, if you're looking at Polaris, remember, Polaris is at the end of the handle of the Little Dipper. That one, the light that you see tonight, left 700 years ago. Alpha Centauri, which is our closest star after our own sun, it's 4.3 light years away. So the light we see now left 4.3 years ago. There's some debate that since it takes the light so long to travel, are some of the stars that we currently see tonight actually dead and they are no longer illuminated? So back to your reference table, page 15. If I have you find our sun, and we're looking at what part of the life cycle the sun is in, you'll notice it says it's in the main sequence. If you look at the main sequence, it's that curvature of dots that goes right along from the bottom all the way towards the top. With that one, you'll notice there's a variety of color, there's a variety in luminosity, and there's also going to be a variety in size. Your supergiants all the way at the top, those are huge. All right? Our sun will never be a supergiant. It's too small. Dwarfs are all the way at the bottom. They're a lot smaller. They're about the size of the Earth. All right, since I just brought up the life cycle of a star, it's on parts of it are on your reference table. So the first part a star goes through is a nebula. It's your gas stage. There's not a lot of gravitational attraction between those particles. Composition-wise, 70% hydrogen, 28% helium, and 2% heavier elements. Now, it has a neighboring star that explodes. That energy that it gets from the exploding star actually causes a greater gravitational attraction between that cloud of dust and gas. With that, those things get closer together. Closer together, the greater the gravitational attraction. Once it starts getting close together and it starts to spin, you get into the protostar. With that attraction comes friction. Friction gives me increase in temperature. So increasing my temperature, I got friction, I got pressure, it's going to contract for millions of years. Once the core gets to about 10 million degrees Celsius, nuclear fusion begins. Once nuclear fusion begins, the star is officially born. Now, reminder, fusion, I'm taking two atoms, a hydrogen and a hydrogen, and I'm putting them together to make something more dense. So a hydrogen, hydrogen, put those together, I get helium. Now with your nebula, you can either get a binary star, which is two, or you can get a star and planets, which is what happened to our solar system. The main sequence is what our sun currently is in. This is the longest phase. Scientists think that our sun is about halfway through the main sequence phase. It's going to stay there as long as it has enough hydrogen to fuse to make helium. After that, what's going to happen is you run out of hydrogen, it's going to contract, all right, due to lack of fuel. And then with a contraction, you actually get more friction. You're increasing your temperature in the core. With that, it causes it to expand. So I get my giant, or my supergiant. Well, for us, it's going to be a giant, because remember I told you, our sun, too small to be a supergiant. So if I'm looking at the giant, it's about 10 times larger than our current sun. Supergiants are at least 100 times larger than our sun. Debate with astronomers is, when it does get into that giant phase, will it incinerate the first 3 planets, or incorporate the first 3 planets, or will it just incorporate the first 2? But don't worry, we won't be around to find out, because that's about 4.5 billion years away. Once my giant or supergiant has run out of fuel, they lose its outer gas, it just got the core. I'm going to collapse inwards, all right? I'm going to get my dwarf. Now your dwarf can shine for billions of years. Or what can happen is it gathers energy from another star, accumulates that, and then it causes a buildup and it explodes, and I am into my nova or supernova. If it was originally a giant, it'd be a nova. If it was originally a supergiant, it'd be a supernova. That gives me all that gas and dust once again, and then I would circle back to nebula. So that's its entirety. Big Bang Theory is a theory of how the universe was actually created. Thought is that all the matter that's in the universe was concentrated in a small area, and that matter got dispersed throughout and making our galaxies, making our solar systems and our planets. So the whole idea is for that one, we're looking at cosmic background radiation. So if I'm looking at the bottom, you'll see on that picture is actually radio telescopes. So they're looking for evidence of background radiation. So with that one, the newest number is that the universe is 13.8 billion years old. Before, if you're looking at Regents questions, before more, greater technology, there was a range between 13 and 17 billion years old. Now with technology, they rounded down to around 13.8, 13.7 billion years. All right, constellations was a vocab word for you. So remember, it's a group of stars that take on an image. If you're looking at your constellation, you'll notice that they shift a little bit westward every night. That's because the Earth is revolving. Your frame of reference is different. Your constellations are based on Greek mythology. The brightest star in the constellation is your Alpha. The second brightest star is your Beta star. I will put some constellations, videos of constellations for you, or websites of constellations for you to look at later on. Personally, I don't see how they come up with some of these constellations because they don't take those images to me. We need to talk about what's the difference between an asteroid, a comet, a meteor, meteorite, meteoroid. Asteroid, that's a fragment of rock. It's orbiting the sun. It's found in between the Jovian and terrestrial planets, or also known as your separating between Mars and Jupiter. Its composition is mostly carbon. Then you got iron and nickel, so it's going to be a little metallic. It's got silicates. Remember, when we did your minerals, silicates had silicon and oxygen in it. Asteroids are going to orbit in ellipses or ovals. And our largest known one is Sirius, is approximately 1,000 kilometers in diameter. Where a comet, I'm looking at comets, ice, dust, methane, and ammonia. So this one, the core is usually rock, metal, and ice. It's going to also orbit our sun in very extreme ellipses. When the comet gets closer to the sun, the ice melts and you actually get a tail. The tail is positioned 180 degrees away from the sun. So I'm sure you guys have heard like Halley's Comet, which you see it's every 76 years. The last time it was there, we saw it was 1986, because I actually did see that one. There's the Hale-Bopp Comet, which won't be around, I think, for thousands of years again, so that one's a miss. But really quick, so I'm going to draw my ellipse. Here's the sun. If the comet is here, as it gets closer to the sun, its tail is going the opposite direction. Alright? Opposite direction. Tail is going the opposite direction of the sun. So it's 180 degrees from the sun. Meteoroids. Alright, it's going to be smaller than your asteroid or your comet. These two are rocky. Iron and nickel. Meteor, meteorite, meteoroid, all the same object. Its location is what makes it different. A meteoroid is out in space, hasn't gotten into our Earth's atmosphere. Once it enters our Earth's atmosphere, it's a meteor. The atmosphere causes it to start burning. On your stream, in April, I put up your meteor shower. That was in the middle of April. So you go out to watch it. So you're actually, common term is shooting star, but you're actually watching the meteor burn up in the Earth's atmosphere. Well, that's your shooting star. If your meteor does not completely burn up in the Earth's atmosphere and actually hits the ground, that one is a meteorite. So meteor, Earth's atmosphere, meteorites, didn't burn up, hit the ground. Meteoroid is in outer space. Same thing, just different location. Alright, need to talk galaxies. So we start with our planet, then larger than our planet is our solar system. Larger than our solar system is going to be our galaxy. Our galaxy is a Milky Way galaxy. Alright, it's a spiral shape. If you're looking at it from diameter, the average one is 100,000 light years in diameter. It's got billions of stars in it. So with our galaxy itself, it's got billions of other solar systems within. Our solar system is approximately 30,000 light years away from the center. It's on one of the arms. If you're looking at our sun, remember we said our sun is in the main sequence phase. It's there as long as it has hydrogen to fuse to make helium. You're looking at it through spectra. It's 92% approximately of hydrogen. If you're looking at the first picture on the left, it's a solar flare. These are actually photos from NASA. The photo on the right-hand side, you see the dark spots, they're sunspots. Alright, they're actually not heat but cool spots. And they're in a cycle. And they peak every 11 years. With the sunspots, they actually cause issues with communication devices. Your auroras, your aurora borealis, those different greens and blues and purples that you see sometimes, usually we're a little too far south normally, latitude-wise, but you're looking at your solar winds, they're getting captured by our Earth's magnetic field. So they're electrically charged particles that escape the corona, which is the outer part of the sun.